time, and I thought, you know what, mathematics is also culture. That's interesting. And that thought sat in my mind and kind of influenced what I decided to do. I didn't go study anthropology. I went to study mathematics. And a few years later, I was doing NSF research experience for undergrads, and I wrote, I think the first time I actually proved an interesting theorem, we were talking about these recoverable resistor networks, which are like planar graphs, by and large, which you can measure the electricity and these different terminal nodes, and I claim to have proved that if you stick them together at the boundary, then that whole structure can be recovered. If you have lots of little ones, you can stick them together. And I'm mentioning that because that was a theme that later sticking things together in interesting ways came back again. So the next time I did anything related to mathematics, it was in the world of bubbles. Is Tom Hale still here? Yeah, so he's probably seen this paper about double bubbles on the two torus. And there we have certain kinds of bubbles, and again, they're things sticking together with some constraints, in this case on volume. So, so this is the kind of stuff I was thinking about. Then I stopped being an undergrad and went off to become a PhD student in mathematics, which didn't go so great because I got obsessed with the idea of putting mathematical ideas onto computers, which of course you guys are all big fans of that. So I feel comfortable mentioning this to you here. People at the University of Texas didn't know what I was doing, and I'm not sure I knew what I was doing either. So, but this is a fact. X is the group, phi is a map like that. Then as a conclusion, that number 5 is what you spit out as a conclusion. And I even took the time to write out some kind of proofs. Are these formal proofs? Are they quasi-formal proofs? I'm not sure. They're just some proofs of these things. As you notice, many more definitions than proofs, and I think that was part of the problem. But I took a bunch of those definitions and I uploaded them to this thing called Planet Math, which was a website which went online in 2000. And for 1 week in October, I was the top user of Planet Math because I uploaded my 900 things kind of packaged together, so all the things about Lebesgue measure were consolidated. And if we didn't have an article on Lebesgue measure, well, now we did in this kind of pseudo-formal thing, 1, 2, 3, 4, 5, and maybe some sublists and stuff like that. And this didn't go over very well. The situation couldn't last because people objected. They said the thing was not human readable, and in one case maybe not even human written. So there was a poll, could we please just delete these spam entries, and why did they go up overnight, sort of circumventing the usual due process of stuff. So again, thinking back to my anthropological days, I thought, whoa, well, this is an interesting result. And you can't quite see the numbers there at the bottom. I don't know how to tip the projector, but in principle, you could read about this 2JY6XW if you wanted to write that down. 1 week in October. So there was my kind of anthropological experience on Planet Math. They like due process. They don't like these kind of semi-formal things. And this started to get me thinking. Didn't really discourage me from trying to formalize this stuff. So in a course at UT, I started taking courses in the computer science department. And I tried to come up with a representation language for representing mathematical things. And here's 2. In this case, I only had 100 such definitions because I was sort of working on this Lisp-like formalism. So there it was. It didn't really go much further than that. So I left UT for various reasons, because I wasn't passing my prelims, getting too busy getting the computer to pass them for me, I guess. And I started to work more with Planet Math on social stuff. So this diagram came from my first paper that wasn't a mathematics paper. And you can kind of see some people bouncing around in this system, annotating each other's texts. And again, you get this idea of things fitting together across some kind of boundary, so that Article A has some segments and Article B attaches to a segment 1, Article C is attaching to another segment, and so on and so forth. So you build this thing by attaching. If you guys are familiar with Git, this is kind of what Git does. I don't know if Git really existed then. I certainly wasn't citing it, but I'm not saying I invented Git, but great minds think alike. Things grow by attaching, including attaching a diff where you delete things. So this was meant to be a model of commons-based peer production, but also because we were thinking about Planet Math, we were thinking about lemmas. Like if you're proving a theorem, you connect to another lemma, so it's kind of like this graph structure. If you're refuting something, it's got this graph structure. So again, attaching in different ways idea. And a few years later, so I basically spent a good part of this 2000s decade working on a computer system that implemented this Scolia-based document model. In fact, I demoed it way back in 2005, but I spent a bunch of time as a hobbyist programmer in this, thinking about things in terms of graphs and their relations. Ultimately got me a new place and a PhD at the Open University, and this kind of boils down my proposal in a nutshell. If we could model some relationships with these triples, like you guys would call it an aubergine, I think. Aubergine in Mexico transported by truck to the aubergine in Massachusetts. If that operation produces smog, you get this idea of modeling triples as reified things, and you can start to reason about them. Here's a more mathematical example. Given the problem of finding the average of three things, this operation, writing three numbers like this over three to get the answer, subliminally reinforces good use of parentheses in sums in general. So my proposal was to model learning using online resources with all these RDF-style triples. In actuality, that isn't what I really did in my PhD, as you might guess from looking at the last slide, a little bit too vague. The question was, Planet Math had basically peaked in interest in 2006 or so. This was 2010 when I was starting my thesis. And we were thinking, well, there's Wikipedia, people are quite happy using that. Maybe Stack Exchange was starting to become a thing. So Planet Math as an encyclopedia was no longer going to cut the mustard because everyone had kind of gone off to use Wikipedia. So the question was, what's needed to transform this peer-produced digital library and mathematics reference resource into what I call the peer-produced peer learning environment? And again, just thinking back to the bubbles or the graphs, you have this idea of people sticking together across some kind of boundary where across that boundary, one person is a teacher, the other person is a student. You could build these kind of big clusters or networks where the kind of flow of information goes through this peer production thing. So a peer-produced peer learning environment means people getting together, answering each other's questions, and learning in the process. So to work on this, we rebuilt Planet Math using a modern infrastructure, using Drupal as the basis and a bunch of semantic web stuff to make it work, and did some user studies with that deployed system, which distracted from other more AI-oriented questions, but we built the thing and got some human feedback. And kind of the key take-home point from the thesis was, let's not actually try to build a competitor to Wikipedia or Math.Stack Exchange or Math Overflow at all, but let's work together, kind of building this mashup social machine and using these things as collaborators. After all, they all share the same license as Planet Math. And so that's kind of brings me to today, because we haven't done that really yet, but that was a take-home point from this process. And this I'm going to just throw in. While I was working on my PhD, I got distracted not only by rebuilding this website, but by editing this book, the Pedagogy Handbook. So these ideas about peer learning don't just apply to mathematics. It could be other domains where people learn about something together. And this is a quite classic thing, but we thought if we could make a handbook, then maybe people could start doing this about new and different things in more exciting ways. And I also want to just take a little bit of time on this slide to point out one of the big problems with Planet Math in the new implementation or the old implementation is you've got this kind of division of labor between users and producers of the thing. And that works okay in a commercial setting, maybe where the producers charge some money, think Mathematica, they're not just building that as a hobby. So it's good to have a distinction because you've got this nice company with a boundary around it and some clients who use their software and pay them some money. But in this kind of open source model, pure production model, the real question is, who are the users and who are the producers? And there's kind of these two communities, one being the programmers who've got to learn something and achieve something and write some papers or whatever they do to get credit for their work, and then there's the users. And so there's kind of a pedagogy problem here. How do you, if the issue is building a pure learning environment for mathematics, are you really going to get mathematicians interested in that or not? So similar in a way to some of the questions that have come up around here about how can we get mathematicians interested in formal proof, but this is informal system building stuff. Okay, so that's a little bit about me. And I'm going to bypass my previous postdoc where I did also some stuff related to mathematics and just catch you right up to today. In Scotland, I presented in detail this paper towards mathematical AI via a model of the content and process of mathematical question and answer dialogues. I'm going to just blaze through that to get to the main example. But this will warm you up to the kind of representation stuff that we're working on. So now we're looking at Math Overflow. There's some tens of thousands of questions, many of which have answers. And the question one could ask about this resource or the sort of junior version of it, the math.stackexchange.com, what would it take to do machine learning over this data set? That's a natural thing to do. How could you apply that? Well, you might want to answer questions or make a recommender. And I will controversially state it's even more interesting to ask new questions, not just answer them automatically. Why do I think it's interesting to ask new questions? Because Turing says in this thing which I referenced, why don't we build a system in which machines talk to each other to sharpen their wits? So now we've got kind of pure learning environment for agents or bots. Or you would if they were able to ask and answer questions intelligently. So in order to get anywhere with this resource, we have an approach. We have something called inference anchoring theory plus content. What is inference anchoring theory? Before we get to that, that's an argument modeling technique. And an example is here on the slide. If Bob says P, you kind of got a model of P floating around, and Wilma says why P. This is viewed as a challenge to P, possibly undercutting the validity of P, but Bob comes in and says Q, which supports P and kind of knocks that challenge out of the way. And this is just rooted in dialogue norms as a way to build up a model of the logical content of arguments. Inference anchoring theory plus content takes that and it connects the logical inferences to some mathematical content, which has its own purposes and it has some constraints. Like, in my earlier slides, if you know what an abelian group is, most mathematicians will agree about that. And so, P and Q, if they have things to do with abelian groups, for example, will have their own logical connectors between them, independent of what Bob and Wilma might say about them. So here's a little bit of an orientation. This is by no means the whole language, but what the heck is this IATC thing? It's a bunch of things we call performatives. These are the ones in yellow, where people can assert or agree or challenge or retract or define or suggest things. And then there's these intermediate relations of which I've only put 3 exemplars to say things like object O has property P, or here's a strategy that can be used to prove statement S, or statement S is beautiful, etc. So this is a complete list of the performatives and a very partial list of these intermediate relations. The lowest level relations are ones like you might find in a typical formal model of computers. So that's a little rundown of what's in this IATC. Let's quickly go to an example. So this is the example I dealt with in detail at Kickham. I've seen this problem. If G is a finite group and H is a proper subgroup of G with finite index, then G is not equal to that thing. Does this remain true for the infinite case also? Full stop. But it's really intended as a question, and that's what it looks like with this IATC diagram. So you've got. So this is the case that's considered to be true. G is a finite group. You've got this conjunction. This implies such. That's asserted to be true. This implication is asserted to be true. And then someone else is asserting there's an analogy between this case and this case. Okay, and one knows probably that G is not the same thing on both sides of this analogy. It's kind of a placeholder. So in one case, G is an infinite group. In one case, G is a finite group. But that also tells you what is the analogy to look for. And then the question is this implication actually true? So this was an initial sketch of what IATC can do for you. Again, these are the statements here on the right. And then these performators are the yellow blobs introducing these things into the graph. So someone makes the obvious comment, is there something I don't understand? Perhaps you mean GHG instead of that. Okay, so now we're going to correct the picture. So people are building up this graph in sort of in synchrony with each other, or at least in this kind of process, right? So here's the new statement. I don't understand that we're challenging this assertion, saying this isn't actually true anymore. It's not true that this implies this. That doesn't even make any sense. And instead, what would make sense is if we reform that to that, and reform that to that. If you imagine kind of canceling out the things that don't work, now we have a revised statement that makes a bit more mathematical sense. And so this challenge, that's kind of an argumentation theory term to say I'm undercutting this, but we want to retain some sense that maybe the graph is right. So it's not completely clear that this relation of a challenge is quite the right picture here to convey the argumentation structure, but I hope you get the idea from the picture that the person is revising the statement of the problem, and there's something new on the table now. So in the meantime, if you're looking at the timestamps, this was 1815. 1816, someone comes along and says, not in general, every matrix in GL2C is conjugate to an invertible upper triangular matrix, and you can see that if you use eigenvectors, and the invertible upper triangular matrices are a proper subgroup. So there you have it. They've added in this answer down below here, so they're asserting no, not implies, and they assert this conjunction is a counterexample to what you would see here if this was true, and in addition, you would kind of see this implies by solving an auxiliary problem, showing that G is conjugate to H, and even that, they're suggesting a strategy for how you would prove that G is conjugate to an element of H using eigenvectors. Right? So this is a bit of a sketch of what's going on, and I think this is enough of the warm-up problem. I'm not going to go into any more detail of the warm-up problem. There is more in the paper. Basically what they do is they go over, if you're very observant, you'll notice that this answer has some problems with it. What the people do in the further discussion is they keep revising the statement of the question until this answer, roughly speaking, actually makes sense as an answer to a well-formed question. So as you see right here, it's an answer, but considerably more fine-tuning of just what is the question being asked has to be put forward in order to make this question, make the answer make sense. It looks like it makes sense, which is why it's treated as an answer here. It doesn't quite make sense until they refine the question.
I'm not sure I follow what you're saying.
Okay.
You say until the answer, the lower part makes sense
Yes?
per se or makes sense as an answer.
As an answer.
Okay.
So they keep refining the question until it's kind of, they're docking
until
it.
it can be the answer to the question.
That's right, yeah, until this answer actually makes sense as an answer to the question. And that's all written in the paper, which I cited, but I'm not going to go into it. But if you're familiar with Math Overflow, you see lots of comments, and most of the dialogue is going on in these comments rather than answers and questions, right? So we've got this answer, or the question, people saying, yeah, but that's not quite the right question. What they want to do is they want to get the right sense, because he asked this quite general question. In the infinite, does this hold in the infinite case? And the question is really, what's infinite? Is it the index that's infinite? Is it the groups that's infinite? And so this is the stuff that gets refined. Oh, maybe we mean in this infinite index case, not just finite index case and stuff like that. So we have to adjust. Basically, this GLTC has an infinite index, and that's the key point. Why is it a counterexample? But here we've said it's a finite index, so it has to be moved into shape. All that just gets adjusted with more comments. We modeled by hand some of the discussion of one question, and in the next part of the talk, I'll show we've done a bit more than that with other stuff. So you can see the Kickham paper for further refinement of the questions like we were just discussing. Supposing we wanted to scale this up to like cover all of Math Overflow or all of math.stackexchange.com or some more of it besides the one question, well, we would require some automation for that. And incidentally, why Math Overflow and not math.stackexchange for this first example is because I was interested in the dialogue structure, and Ursula wisely pointed out that people on math.stackexchange.com aren't necessarily going to be asking and having the most interesting questions. It's more like, how do I do this? And then someone tells them how to do it. And so there's going to be less of this kind of informed discussion. Even so, one could still model what goes on in those more simplistic cases. It's just less interesting from an argumentation standpoint. And so there's some relevant prior work. Most interesting for me, I think, is the fact that the 100 most frequent schematic patterns like let X be a Y cover half of this somewhat constrained, stylistically constrained, but by no means formal corpus. So the hope would be that we could find more patterns like that, which cover schematic statements. And we were just looking at some of the stuff one can do with modeling language earlier today. But also looking at the patterns of dialogue. So, what does it mean? When does someone put in a counterexample? When does someone decide to refine the question in order to get that to align to the answer, etc. So argument mining is this new thing, relatively new thing, but it's taking off both here and in Germany, that seeks to identify inferential structure in documents. What is the argument here? And I've just mapped a little bit of one example for you. Okay, so and here just as a complete bonus for paying attention to this talk, SE match is a computational challenge problem. If you're thinking, oh well, what do you get from automating this? Well, maybe you have a good solution to this challenge problem. So the challenge, match existing questions and answers selected from the Stack Exchange network. And to make this like a fair contest, what you could do is you could ask people to submit their systems 2 months in advance. You collect a bunch of questions which they've never seen before, and then you ask them to match the questions with the answers, or the answers with the questions from this sample set which they've not seen, and get trained on all the previous examples. So that's what this business with the coins down below is meant to show. It's a little bit like the card game where you're by memory flipping things over, and you say, oh, here's the cat, here's a pile of bricks, here's an elevator, here's a cat. Gosh, where was the cat the first time? This is the same kind of idea. Of course, you would see that this answer maybe would be on the flip side of that Q and A go together, but because you're blinded, you don't know which things to look at. And I would compare this favorably in a sense with this Vinograd schema challenge, which is another challenge problem, of which I'll just give an illustration by example. You have to resolve this. The city councilman refused the demonstrators a permit because they feared violence. So we know who they is because we're smart. If you were a computer and you were asked, is they the councilman or is they the demonstrators, you might not know unless you'd studied some common sense stuff and modeled that. So I claim SE matches as one advantage over this Vinograd schema challenge, because we don't need to be smart per se to come up with these things. We just let the crowd come up with our challenge data for us. So that's SE match. Okay, so now on to the title of the.
Excuse me,
Yeah.
Twin too fast. Can you go back to the previous one?
This. Absolutely. Maybe I should take a.
Have you done this? Have you?
No. This is a purely theoretical
Well,
proposal.
this seems really a lot like machine learning 90% doable, because you are not generating the answers, you are just classifying them.
Absolutely. That's what this is meant to be. Anyone can come in and play, but in principle, if once we come in and play with this thing, then the IETC stuff could help us get the last mile. So I think the low-hanging fruit is just by machine learning, building up a nice model of what's going on might help you get.
I think you might really need some sort of adversarial setup to try to fool the machine learner with a fake answer which looks symbolically very similar.
Yeah.
Because otherwise you will learn only very simple distribution of characters. That would be my sort of guess.
Yeah.
That
I think you should have mutations of the correct answer and the correct answer. The challenge should be to find the correct answer.
That's a reasonable suggestion for a variant. I mean, that if it's not hard enough, there's other kinds of similar problems one could look at. Sort of like they'll have multiple answers, so they're much more semantically ambiguous with each other. But then you want to rank them in the order of their empirical upvotes. That sounds a bit harder. So now we've got this. It's not just apples from oranges, but now we've got to tell the different kinds of apples from different kinds of
So
apples.
when you want to rule out, things like keywords and stylistic things.
Yeah, and just learning from the categories and stuff like that. But I would say that using these variants, you could make it harder, perhaps not arbitrarily hard. And again, if it proves to be too easy, then we just start generating answers to questions and to test using humans, whether it's actually a good answer.
it probably will be easy, but getting it up from the 90% to 100 will not be easy.
That's what I'm saying. So I was meant to give people a sense that anyone can play, and kind of like this Vinograd schema challenge, you can get a good part of the way using machine learning. So indeed, that is the idea here. When I was at HCON, I saw the latest contest with Vinograd schema challenge, and they already have pretty well performing ones on these things.
No, I'm a bit lost. What is the expected gain of doing this kind of experiment?
Well, so the Vinograd one, it's meant to model somehow the ability to model common sense reasoning inside of a computer. So another example from that is the hat would not fit into the suitcase because it was too big. We know it wouldn't fit because the hat was too big rather than the suitcase being too big, but we know that because we've got a bunch of common sense knowledge about container relations. If you're a plain old boring computer, you wouldn't know that unless you've been trained on some common sense stuff. And in this case, I'm saying the winner of this contest, or if we did it yearly or something like that, would have to have more and more domain knowledge in whatever domain you're modeling.
Okay.
Mathematics in this case, but it could be other subsites of the Stack Exchange network. And the gain is that it's meant to be a training camp for systems to build up that knowledge so that progressively then you would see that things that can compete at this should also then be able to go into the more interesting challenges that I put before, asking and answering interesting questions. Like they may say, oh, I can't tell the difference between these two, and that could become a question. You know, why did you say category theory here as opposed to category in some other sense there?
Actually, another thing you could do is remove the timestamps and ask for them to be sequenced.
Yeah, that would be similar. That would be a good one, similar to the rating, empirical ratings of upvotes. But yeah, absolutely, that would be a pretty fun one. That would require you to understand some of this argumentation structure that I was outlining, not just the content. So yeah, that would be great. Yeah, good idea. Okay, so modeling the way mathematics is actually done. So this is another paper, kind of the sequel to the one that we've just blazed through very quickly. It's also available online. If you could read, you could download that. So recently accepted paper we've drawn on something called conceptual dependence theory and a novel reflexive representation strategy to design a prototype system in Lisp that can represent and reason about IATC diagrams. And before you guys all go about running in the street and opening bottles of champagne, it's just to get the weighting right. We've designed the prototype system, but the actual implementation of the prototype system also exists. That's what it means to be a prototype system, but it's not like, oh, we've solved all of the AI problems in mathematics. It's very preliminary, and I'll show you that. Okay, so here's another example, which actually is quite long, and if you've ever seen this in the paper or printed out, it's like a long scroll, but I've just broken it into pieces to fit onto several slides. So this is the top part of it, and I've taken away the colors. Now the training wheels are off, it's just black and white. But you're used to having now the dialogue stuff going on the right. In this case, it's Timothy Gower's 2012 Maxwell Institute lecture, and it's being mapped to IATC. So we can take some time to read through this one, having rushed. I think I've got a whole hour or half hour now to take on this part of the talk. And of course, there's time for questions and I guess discussion in a whole other hour if you guys are up for it. But anyway, so we'll go through this whole proof just so you know and don't feel cheated that there was actually no mathematics here. So he says, what is the 500th digit of that? Looks kind of hard, especially if you don't have a hand calculator, or even if you did have a hand calculator, it might be a bit hard. Nevertheless, he says even this, eventually a computer will be able to solve, so we've taken that as a challenge. For now, notice the total stuckness can make you do desperate things. And by this point, I'm starting to parse this stuff a bit, using some of my own human intelligence to say, this looks like a throwaway joke, a kind of a line, oh, total stuckness can make you do desperate things. But maybe this is suggesting a strategy, which is if we could simplify and compute, maybe we could actually simplify something. So this kind of goes on. Furthermore, knowing the origin of the problem suggests good things to try. The fact that it's head of the problem is a huge clue. So this says that it should actually be fairly straightforward once we find the right trick. These things then inform this next line, which otherwise would sound like it came out of the blue. Can we do this for x plus y, for e, for rationals with small denominator? And you're familiar with analogies because I had one in the previous example. I'm now asserting that this thing is somehow analogous to this, right? So we just swap 2's for x's and 3's for y's. Maybe here there's another analogy where we swap what's inside the parentheses for e, and another analogy for this thing with these rationals plugged in. I'm sorry, it's cut off. This is just the nature of it being a huge thing. How about small perturbations of these? Maybe it's close to a rational. And here I want to draw your attention to the fact that this thing, for the rationals, we can really compute this. So this has a property. This is stuck in this dark, bold things are like heuristics. Oh, we can really compute this. The 500th digit of that is 0. So that's pretty cool. So we've actually found something that we can compute, whereas the previous thing was looking pretty hopeless. Small perturbations of these, this is again suggesting another strategy. The trick might be it's close to something we can compute, right? So this strategy has a dashed line going down quite a bit further down because we'll actually use that later on. So we'll follow the advice of this strategy. Some of these other strategies are kind of throwaway things that has a property a computer could follow it. Okay, how do we actually use that? I don't know. This should be straightforward once you find the trick. Maybe there should be a dashed line out of this too. So that,
Again, I'm a bit lost. The right part of your slide is the actual text, and
Yeah.
the left-hand side graph is what you construct from the text.
you're not lost. That's perfect.
Oh, sorry.
Okay. Yeah, exactly. And this is all by hand. I've done this using my own native intelligence. There's no automation in this. I just drew the picture. Right? So yeah, the trick might be as close to something we can compute. So then this, I would also claim that previous chase through these different examples, can we do this for x plus y for e rationals with small denominators, somehow representing an inductive search process. In other words, we're trying to find the right pattern, the right level of generality in which to address the question here that we could actually do something about it, right? Something that we can actually compute. So mth digit of that, well, that's still too hard. How about this? We take m, I don't know, but just n is equal to 2. So this is looking pretty simple, right? So we've generalized and now simplified within this generalized space to find something we can actually compute, right? So that thing, this is just written on the chalkboard, say assert this, and there's some other kind of algebraic thing. This thing here instantiates this general form of the problem. We can actually compute this. This thing expands. I've got to go to the next slide. There's just sort of algebra stuff here. This expands into that. And now, sorry if I'll kind of back and forth between slides, but again, this thing is now written on the chalkboard. That plus that is equal to 10, okay? So we computed that. We found these cross terms. Why are we writing this thing? The suggestion, unspoken here, is that we're going to eliminate some cross terms, right? So we found that plus, well, we found that plus that. This thing here sums to 10, okay? This expands that, and this sums to 10, which is an integer. And this is basically eliminating cross terms. Actually, the binomial theorem is how you eliminate cross terms in general. Now you've got 2012 instead of 2, but because we're eliminating all the cross terms, because that thing's got a -1 sign, we're now using this strategy, both sort of suggesting and using this strategy in one go to eliminate all the cross terms by the binomial theorem. So now know this thing is an integer, and this thing, this little correction term is a very small number. So maybe the final answer is 9. Hope you guys are following the proof so far. Okay, we're getting pretty close to the end. But this is the interesting.
We're more interested in the problem than in the graph. Actually.
That's cool. Yeah, that's cool. I think that's fine. That's why it's here. So but this is where the graph gets a bit interesting. So I'll jump over that. So okay, so this is a very small number. Maybe the final answer is 9. Remember, I told you about this dashed line going all the way back up to the top. So I'm saying this stuff, which I'm indicating with this arrow, which doesn't actually point to anything specific. This is like a lasso. So I'll try to, it says, nota bene, pointing to a subgraph. So this is the subgraph. Some of it's on the previous slide. That really can't be helped. But this is basically what you would normally think of as a lemma. Okay, so this thing implements the suggestion way back from here. The trick might be it's close to something we can compute. And lo and behold, this lemma does the job. This thing is small, we can compute the other thing, we've been over all that. And then there's this kind of floating strategy hanging around suggest. Numbers that are very close to integers have 9 in many places of their decimal expansion, okay? So this is kind of what was already said, and now we're deeming that to be a strategy. We found a new goal. Let's prove that integers have 9 in many places in their decimal expansion. And I don't know that you guys had time to write all this on the chalkboard, but we actually need to check whether it's small enough. So you look at this, it's smaller than this, which is equal to that, which is equal to that, which is smaller than that. So we're in luck, okay? So this kind of chain of equalities, which Lamport, I think, in his structured proof has a special way of writing down chain of equalities, but again, I just put this as a nice circled subgraph here. This stuff, all these different things are asserted, and this chain of reasoning implies this thing has at least 503 nines in its decimal expansion. And in particular, we specialize 503 to 500 to conclude the answers in D9. So I hope you don't feel cheated because we walked through at least one proof and it wasn't an uninteresting one. I also want to mention, just again in terms of the diagram, at least one relevant edge of interest isn't drawn. So I have these arcs coming back to say which things implement this, that implies, maybe, oops, sorry, I'm going wrong now. This implies should have a kind of backward link saying, yes, this new lemma is implementing this strategy. But something else is, this strategy is basically just not connected to anything. It kind of pops out of nowhere. And I will correct that in the next part of the talk. Okay, so how could we reason about the thing I've just shown you? We've got this graph, we've got this mathematics. How could we reason about it computationally? So again, it's worth pausing here to think, oh, well, if you're thinking, I'll write this thing down in my favorite formal theorem prover, I hope you will. That would be really interesting to see. But I think it would lose some of the details from way back here, because this is simply not deductive reasoning at all. Total stuckness can make you do desperate things. This isn't something you're probably going to be able to formalize in a typical deductive theorem prover. It's maybe a bit challenging to think about how to formalize it in general, but this idea of doing a search by analogy is an inductive search at that is one idea. Now I'm really going back the other way. Sorry. So how could we reason about this in computation? So there's this thing, conceptual dependence theory, and there's a picture here. So what does it mean for John to sell Mary a book? Well, John gives Mary a book, Mary gives John some money, and somehow the fact that Mary gave money to John causes him to give the book. This is a kind of schematic thing. In fact, here this is some Lisp code again, back A trans of actor, object, and recipient. So it's A trans is this, and this is a frame. Here's my other frame, quite similar. I haven't bothered to write down the IR because I don't know how this is meant to be represented. But again, we've got this kind of relation between relations, which we're at least familiar with from the other setting. So it's inspiring. Why? Because this conceptual dependence theory can reason about little stories and story snippets like this. John went to a restaurant, he sat down, he got mad, he left. Why might he have gotten mad? Can anyone guess? Anyone want to hazard a guess? Are you as smart as an AI program from the 70s? Any guess?
And no food.
No food, that's pretty good. I think the official answer is the waiter didn't come. But yeah, no food. It's good. But here we have another hungry person. She was hungry, she picked up the Michelin Guide. Why? Anyone? Yeah, that's it. So it can reason about that and come up with these kinds of answers, using obviously a background knowledge base about what goes on in restaurants and how people eat things. And they've got, so I put A trans here as one relation. This is giving something or transferring something to someone else, but there's a bunch of other relations about eating and things like that which you can reason about. So now we replace those A trans things with our good old familiar asserts and suggests and those other performatives, right? So we have primitives, they're called in CD. Now we've got asserts and suggests. So this represents a little snippet, that one where I first said it was interesting, where we've got a subgraph. So I've just stuck in this subgraph implements. The trick might be it's close to something we can compute. Remember that was the thing at the top end of the dashed line that I was making such a big deal about. And then we got this strategy here, which is, again, I told you this was sort of floating around. Numbers that are close to integers have 9 in many places of their decimal expansion. No, very close integers have 9 in many places of their decimal expansion. So 1.999 500 times is very close to 2, right? And also that may have some zeros, but the interesting point is to find the number with lots of 9s and then subtract it. Well, we were asking what was the digit, so it's 9. Anyway, there is 0 from the other side, yes indeed. So this is close from the left, I guess that's the point. So it should say close from the left. Lo and behold, the strategy I told you about that was just kind of hanging around is this why not do this thing actually comes out of some more or less known facts. So on the one hand, we know that n is close to m, and m is an integer. This implies n has 9 decimals, 9 is in its decimal expansion. And on the other hand, we know this thing has property is small. If you put these together with some other background facts, these things were just floating around in my previous diagram, but you need to supplement it with some additional background facts and some inference rules. then you get that suggest statement out. And I'll just walk through real quick what that means. But this would basically show you that that suggest thing, which is floating around, isn't floating around. It pops out of the reasoning, or pops out of some quite plausible reasoning about things that are already known in the proof. Okay, so how might that look? Well, we've got these assertions, like in the picture, A as property this is small, B implies this, right? These are just our local assertions. These are things that might have had to be programmed in, that 0 is an integer. If n is an integer, it's computable. C is equivalent to this, they're close to 0. And this is what we're going for here, viable strategy, this, okay? So here are some inference rules, simplify. This has property plus implies, some kind of transitivity of implies, and we can weaken equivalence to implies. And this little representation language is allowing me to kind of take a picture of a graph, represent it inside of Lisp, and then reason about what's going on in these little bits of a graph. So it's like a grammar rule. If you see this stuff, you can replace it with that left-hand side. You see this, replace it with that. So you massage your graph until it looks how you want. And this, sorry, the fonts had to get small, and the last little line is run off. But in any case, you apply these inference rules to the graph as you could imagine drawing it, or as the system has it programmed here. You apply it. You want to get this conclusion. These are the things you pull out of the graph. Triples given the beginning and middle. You've got your vertex, which is this suggests node there, and yeah, lo and behold, you can pop out F as the conclusion. Okay, so this is where I wanted to clarify. This means designing a prototype. We have a prototype, but this isn't quite implemented yet. Should be by the time we go to present the paper in September. But the other point is, the key thing is, this was specified by hand. So we did all the reasoning, and this is only just showing plausible representation. It would take a higher level of reasoning to kind of search around and assemble the right inference rules with the right data to get the right conclusion. So this becomes a kind of search process, to put it loosely. So lots of directions for future work, of which I will only kind of talk about a few of them. So formal proof. This is kind of the main subject of big proof, I guess, or one of the more main subjects than informal proof. So wouldn't it be quite nice to demo the system walking through a proof like the one we just discussed, or perhaps a mini polymath dialogue where you get these dialogue loops that are kind of actually very natural because people are refuting and arguing with each other. Well, this would probably require refining the IATC representation language somewhat, and coming up with more of these CD style reasoning moves. So we've put in three inference rules. You'll probably want quite a few more to plausibly represent the moves from one thing to another. So let's be clear that IATC represents what people say, and this IATC plus CD theory represents how you move from step to step. So it represents not just the reasoning that goes on in the dialogue, but the effective or plausible reasoning about how you get from step to step. Wouldn't it be quite nice to integrate some external SMT solvers, proof checkers, proof systems, computer algebra systems, so that things like x sums to some integer or x contains a sum and y could be treated by appropriate systems. Perhaps this is more of a proof theory thing where you want to prove that it sums to some integer. Here you just hand it off to a computer algebra system which says, yep, there's the sum end in there. So we don't have to necessarily build everything if we can integrate these external systems. Well, okay, how about we take it a little bit further, build on the CD theory to reason about embodied intuitions in geometric problems, because after all, this is a kind of algebraic one. So, as Joseph said in the talk earlier today, what about diagrams? So supposing you had a diagram, what do you have to reason about that? And maybe we could even connect that with previous formal approaches in geometry, but one thought would be to have some kind of informal modeling. And that might sound like a complete reach, and I think it is, but at least it's a natural reach from CD theory, which is again reasoning about issues close to things like containment, because someone eats something and stuff like that. So maybe it's not a complete reach to build a kind of CD theory with the lack of conceptual metaphor information. And then we've done some reasoning about hypergraphs. Well, other people, including Matea, here have reasoned about diagrams, so maybe we can map some of this reasoning about diagrams stuff to reasoning about hypergraphs. And on that note, I just want to comment that you know, that as Mateus pointed out in her talk on these accessible reasoning with diagrams, it's spatial, whereas these hypergraphs, kind of we lose a lot of that sense of space. But we don't lose all of it because we've got these things I would call cones. I don't think I used that term, but that's where you're lassoing some part of it. A normal formal proof, we call that a lemma. In this case, we're like drawing a line around that stuff. So we've got at least a bit of a sense of space inside of this graph, which you don't have in a purely graphical theory where it's just a network and all you've got is your network topology. So there's a bit of a sense of space going on inside of these diagrams. And so there's a bit of maybe a sense of some embodiment interaction. So linguistics would be a natural thing. So parsers, could we generate this IT plus C plus CD automatically? Maybe initially via an intermediate semantic markup. And again, today we saw some thing sort of like that, but here I'll put a reference NKS for S-Tech, for Michael Kohesi, S-Tech. What about this IT specification? As I said already, this should be understood as preliminary and refined in corpus studies. Maybe we can use statistical methods on some relevant corpora. Expanding on this, let X be a Y thing, as I guess I already discussed before. But again, it's using now a data-driven method as opposed to a by-hand coding method. Machine learning is indeed a kind of very much on the table thing. Could we integrate this with knowledge bases of mathematical terms and frequency data established by the previous point? I was just talking about what kinds of things do people say and how often do they say them. What are the things they talk about? And if you remember way back to the introductory biographical part of the talk where I had this kind of database of list-like representations of mathematical objects, kind of frames of saying, you know, what does it mean to be an abelian group, or what does it mean, what is this theorem? Maybe we can integrate with some of those pre-existing knowledge bases. Wouldn't it be quite nice to model stack exchange dialogues? That was what I was talking about in the middle part of the talk. And there's been some work on Reddit discussions. That's, you know, like just modeling the follow-up structure, not this detailed argumentation structure. But it's a bit of argumentation applied to the Reddit stuff. So inspiring the fact that they can at least do something. And again, the big motivation here is to do what Turing said we should do, build a system with multiple agents that can converse with each other to sharpen their wits. So again, a kind of pure learning for machines thing. So here's some recommended reading. I include myself, I haven't even read all of these things, but here's some things one would want to read as a kind of syllabus to approach this this future work. And that's the end of the talk.
Can you get the spec exchange data completely?
Oh yeah, it's there. They've got a nice API to get it either completely or partially, however you want it. You can just download it as a zip file as well. It's there.
So you said it's like 80,000 topics?
Yeah, 80,000 questions
Oh.
on the math of the one.
So is there a plan to eventually build a system that can solve mathematical problems, like maybe to solve the problem that is given there?
Absolutely. So yeah, goes way back here to this motivation. Supposing you're solving a prelim problem in mathematics, or even a textbook problem, or challenge problem. We've seen this, mini polymath thing. Wouldn't it be quite nice to have a system that can do that? And what we've seen now, in the kind of social proof, in the mode of social proof, is we've seen that a bunch of people, if they put their heads together, can solve these challenge problems, the Math Olympiad problems. And it seems that their effectiveness is pretty good. There's Ursula and Allison have a paper, 74 minutes of mathematics, where a group of people online dispatch one of these challenge problems in 74 minutes. Now, what's interesting about that is if you just take the population of people who actually sit the Mathematics Olympiad, about 25% of those people would solve any given problem. So some of the crowd is smarter than any given individual. But yeah, wouldn't it be quite nice to simulate that crowd process inside of a computer and be able to solve problems? Here's a simple one, but the Gauss one we saw, or these mini polymath style ones would be harder, ones that the formal systems can't tackle right
Oh, okay, Matteo first.
So you had did I understand correctly that you took Stack Overflow, you did those devised those graphs,
Yeah.
and you identified that there was a solution that looked like a solution, but the question was not quite fitting for that
That's right.
solution. So you identified something like a mathematical methodology, like in the style of Lakatos.
Yeah.
Right? So you revise your definitions or whatever. Do you think that you could use this kind of approach to identify other strategies that maybe align with what Lakatos was identifying already, or additional ones?
Yeah, you hit the nail right on the head. That's the kind of ambition of this IATC thing. So we had written a previous paper in argumentation theory, where we formalized Lakatosh's theory, but it's quite constrained. Lakatosh has this kind of player piano or clockwork style of, you do this, here's a counterexample, here's what you can do in the case of a counterexample. You can, for example, monster bar it by saying it's not a counterexample, or you could admit defeat, so yes, it is a counterexample, etc. So you have to do this step-by-step stuff. So we throw away that scaffolding here, but we retain kind of the lexical abilities inside of that. Like, again, here's a counterexample. It's just we're no longer constrained to say, oh, then here's how you have to follow up. People can follow up in different ways. And one of the things Lakatosh doesn't do is, you mentioned refining the definitions, but here it's a little bit more subtle than just refining the definitions. It's actually kind of moving all the pieces of the deduction into place. So we all agree, you know, it's a kind of sense of defining something, but it's really defining what is the problem that we're trying to solve, rather than what does it mean to be a polygon or something. It's similar to Lakatosh, but one other comment on that note is here, see, in this previous step we had this reform, which is just reforming this sentence here. So it's, I don't know that Lakatosh would quite cover that, but what I was trying to get at before about refining the question that we're asking is, in a sense, what they're doing is they're applying this reform relation to these graphical structures. So they're saying, oh, we're not actually talking about this graph, we're talking about that graph. And so it's somewhat in the spirit of Lakatosh with the counterexamples, but it's not always like that, because sometimes people just make notation mistakes, or they scope things incorrectly.
But that's exactly my point.
Yeah.
Have you identified additional
Patterns.
type of strategies for
Yeah.
mathematical discovery?
I can't say, oh, here's a list of them, but I think that's very much an objective. Yeah, so it's going to hit the nail on the head, but maybe it needs a few more whacks before.
So my question is that, you know, if you look at, for example, classroom settings where, you know, kids tend to have more or less the same questions, that the structure of these, I mean, the questions is predictable.
Yeah.
And could you, for example, then you know, build something that is actually you know, taking the student through these things? Okay, you know, this is.
Yeah. So this. I mean, that's yes, but I think So Matea's question about what's going on structurally inside of there is certainly before we get there. But I think that would be one nice application of this. Like, what's the point of answering questions and asking questions? Well, you could build all of this knowledge into an automatic tutoring system.
If you have a huge data set, and
Yeah.
you can say typically a concept like this triggers a question like this.
Absolutely, yeah. That's the kind of thing that one could do with this data-driven approach, as opposed to the active math approach, where all this kind of intelligence has to be hand-coded. Well, you can do it, but it's going to be a lot harder to consider all of these different edge cases. If you find, here's a bunch of kinds of patterns of questions or patterns of reasoning, which are on the way to the answer, those could kind of intermediate things. Oh, but, you know, did you really mean infinite group, or did you mean infinite index? This kind of stuff. If that comes up a lot, then that's a kind of pattern you know in advance those students are going to ask this kind of question. Yeah.
Ed?
Are the is there any typing on the arrows to stop you from having nonsense graphs?
That's an interesting question. So I didn't mention here about expands, but I want to point out that this assertion is pushing in some kind of relation. So in a sense they are typed, because it's an expands type relation, and then we can just check, is it true that 2 plus 2 square root of 2 square root of 3 plus 3 expands that, so we could check that using a computer algebra system, for example, and see if it's really true. But at the same time, I don't think we want nonsense graphs, but we certainly don't want only graphs that are correct. As we've seen before, people are saying things that are incorrect, so you want to be able to model their incorrectness inside the graphs. You don't want nonsense, but you do not want to insist on some even common sense, in the sense that people might not possess if they ask questions which aren't even questions, which are badly formed questions. And so how do you deal with this? I mean, so basic answer to your question is that sounds good. It doesn't exist yet, but some ways to refine this might be, so for example, here I've just put G as a finite group, but instead of having this string here, you could have an object which would have a type, and that then would have, perhaps a matching type, or some field of it might have a matching type here, so that when you then compute this analogy, you're doing it very precisely over objects, which really exist. And that kind of rigor about the mathematical objects you reason about could certainly kind of percolate up to the graphs, where you're simply not allowed to make an implication statement about things which cannot be said to imply stuff. So it doesn't exist yet, but it's a smart idea, and I think that would be how one might go about it, to build in from the kind of ground up from objects.
I have another question. Where are you using hypergraphs in particular? Because I've only seen arrows.
So here there should be hypergraphs. Here this is kind of wrong. The style of notation is when I've got a big fat bold arrow pointing at something.
Okay.
Here it's not, but these should be redrawn to be big fat arrows lassoing this and lassoing this. So these are hypergraphs in the sense of something that points at a bunch of structure, not just pointing at one thing. There's two definitions of hypergraphs, but that's the idea. So this was drawn before that was
directed hypergraphs.
Yeah. That's right. So one, and in this case we're kind of just sticking, as I showed someplace along the lines here, to kind of first order theory. So rather than having a multi-edge, we're just pointing at lots of stuff. But for example, if you wanted to point at alpha's an edge, you'd be well entitled. This is what A is doing, it's pointing to this edge. So if it was RDF, it would just be a reified triple. And that's the kind of hypergraphs we're talking about, pointing at edges, and then you get these cones, which allow you to point at lots of stuff, but in this kind of first order way. So they should be all over, but in some pictures, I didn't draw them, and then the drawing 2 dimensions. They should be all over, and wherever you see a bold line.
So what exactly is the motivation for using these fancy edges and things, rather than just using standard term structures?
Well,
a term tree or something?
Do you want to say more about what you mean by standard term structure?
Like a term tree. So
Yeah, so imagine you've got a Lamport style structured proof, which is basically a tree. You've got some statement of theorem steps, and those steps become lemmas, and those lemmas turn to derivations. Well, it's all strictly deductive, that's the point. And then you don't get, probably don't get things like these long-range relations where you're implementing a strategy, and that strategy, I mean, you might be able to tag a lemma and say this lemma is based on this thing, but what you really don't get is this, oops, where am I? Here, sorry. Yeah, so this edge is coming into my thing. What I want to be able to do is say, here I've lassoed this stuff, but you can also deal with stuff inside of that. So I'm going to say, here's this thing, and things are coming in and out of that across its boundary. So if it was a Lamport style proof, you have a lemma, but you're going to be unable to talk about what's going on inside of that lemma except to get the certificate out. You put the statements in, you check it, you get a certificate out. What I want to be able to do is reason about what goes on inside of these things, partly because they're going to be wrong, and the proofs are going to be wrong, and a strategy from somewhere else. Like, for example, this lemma is going to be proved by analogy with this other lemma. You basically want to look at that and then do some graph transformations on the stuff that's going on inside of that. And perhaps those analogies are going to cross levels. So that's one reason why. Maybe there may be other better reasons why. But basically, yeah, you don't want lemmas because they're just black boxes. You want these slightly more slushy lemmas, in my opinion.
Thank you.
I guess, yeah, maybe I can put on a Fenner hat and say if anyone wants to stick around and talk about social proof, we can just have a roundtable discussion of that. But I guess you're not
I
obliged.
think you're gonna have to drag people to pubs over.
Yeah, it's up to you. If you want that.
We're all talked out.
Or people are talking, that's fine. I'm not proposing we stay here, but I'm just saying, according to the schedule, Fenner would say we've got an hour, but no obligation to stay.
So can you hit the